Alright, so I am starting to feel the pains of being a YouTuber because I'm going to repeat this lesson for the third time. The first time we recorded it was nice, but the whiteboard looked black by the end of the lesson. Not so good. The second time the microphone stopped working midway. Let me check. Yeah. Not so good either. So in this third repetition, maybe it will not be as fresh, but we must be reaching perfection, or pedagogical perfection. Okay, so it's a very important lecture, so I have to repeat. We are going to discuss discontinuous phase transitions. All right, so essentially we are going to think about the case where we have an ordered parameter, which we will keep calling P, as in the polarization in a ferroelectric, but which in principle could be some other structural ordered parameter, even magnetic. And this P as a function of temperature, or any other thing, this P as a function of temperature is going to do something like this. So it's zero at high temperatures, and then at a special temperature T star, it becomes different from zero. Okay? And of course, this spontaneous symmetry breaking can happen by the system developing a positive polarization, but also similarly by the system developing a negative polarization state that is related by symmetry with the positive one. Okay. So the spirit, as always, is going to be to try to derive the simplest free energy model, Landau model, that allows us to discuss this. We will continue to use polynomial expansion, of course, and polynomial expansion, where around p equal to 0, where we are not so concerned about being in the perturbative regime. We do this essentially for mathematical simplicity and for being systematic in how we can improve our description or add complexity. Okay, but not so much because we think this polarization will always be small. In many cases, it will not, but these models are still very useful. All right, so if we look at this, here we have something different from what we had before, in particular at TC, because at TC we have three different states that in principle are accessible equilibrium states of the system. And that means that our free energy potential at T star, I call it TC, let me call it T star, the distinction will be made clear later. The free energy potential at T star has to have three minima, right? So if I plot F as a function of P for T equal T star, I have to have a minimum around P equal to 0, and I have to have two symmetry-related minima at finite values of the polarization, positive and negative. Of course, we still have the symmetry upon reversal of the polarization, so it continues to be true that this guy equals this guy. All right. And by the way, the structural distortion, also symmetry-wise, or from the point of view of the structural distortions, this transition could still involve a very simple movement of a central atom that was sitting in a centrosymmetric position off that center. Okay, so from the point of view of symmetry, etc., continuous and discontinuous phase transitions, ferroelectric phase transitions, for example, may look pretty much the same, even from the point of view of the structural distortions characterizing the symmetry break. It's very difficult to say from the structural distortion alone, in general case impossible, whether the transition will be of the first or of the second order. All right. Okay, so we want to write this energy landscape. And of course, in the spirit of simplicity, we have to, we know we have to have three minima. What happens in between? Well, we just here choose the simplest, smoothest of interpolations, which would be like that. So the minima are connected by an intermediate maximum. Can only be that way, or this is the simplest way. And then, of course, when the magnitude of the polarization is very large, the free energy goes up. At T star, we need this. from our theory. But we know more things about the material. We know that at high temperatures, the dominant equilibrium state is the one with zero polarization. We are in the paraelectric phase in the case of a ferroelectric, and therefore at high temperatures, the free energy landscape has to look like this. Let's say for T much larger than T star. Okay. Here, by the way, I'm going to implicitly assume that the free energy for the state with P equal to 0 is always 0. But I didn't draw it very well here, but let's make that assumption later when we introduce the mathematical expression. This is not true. This will not be true in general, and doesn't need to be assumed, generally speaking. But for simplicity and for the purpose of this lecture, let's live with that. Okay. And the third thing that we know about our system is that at low temperatures, the dominant minima have the lowest free energy minima have a finite, correspond to a finite value of the polarization. So we can draw them. We can draw them maybe like this. They are obviously coming from those two. And if we try to interpolate here the free energy, well, there are several options. Maybe the smoothest interpolation actually from what I drew would look something like this. Draw it a bit better. Okay, so we could think of an interpolation that also similar to what happens here. We are still at T star, we still conserve three minima, but where the lowest free energy minima are the polar ones. Or we could imagine that this interpolation actually looks like this. Where only two minima survive, only the ferroelectric minima survive. Okay? All right, so pictorially that's simple enough. And now it's a matter of finding the simplest mathematical expression for our Landau potential, which is going to look as an addition of terms at different powers of the polarization. That gives us that. So one key consideration here is that, well, of course, and if we want to find a general expression, we probably should start with the most complicated situation, the most complicated temperature, and then see if that is sufficient to describe the whole thing, right? And here, the most complicated temperature for sure is T star, because we need at that temperature to describe three different minima. And by the way, as you can see, it's obvious I have defined T star as the temperature at which these three minima have the same free energy, but that's not important for us right now. I will come back to that in the end. Okay, so we have three minima in a curve like this. We know that we have 5 points with zero derivative, right? We have 5 equilibrium points. 3 of them are minima, 2 of them are maxima. The 5 of them have a zero derivative. So we need a free energy whose first derivative can give us 5 zeros, and therefore we need a free energy that at least goes up to the 6th order in the polarization. Okay? So then our Fp of t, recalling also that that it has to be an even function of p, can look something like this. P squared too many betas. All right. And now how do we get three minima? Well, so if we are at t equal t star, we have certain conditions for these coefficients, right? Around p equal to 0, alpha defines the curvature there and the curvature of the free energy, and we need to be in a minimum. So we know that for t equal to t star, alpha is positive, alpha has to be positive. Then alpha takes us up in energy, but when the polarization grows, eventually we have to come down. So there has to be a term doing that, and that will be beta, which has to be negative. And finally, to define those minima and for the free energy to be bounded, generally, when we go very big, the free energy has to go up. So gamma positive is what we need. All right. What else do we know? An easy case is this: if the temperature is much larger than T star, larger in general, but certainly, yeah, let's go to the limit just for simplicity, for emphasis. We have a dominant minimum at P equal to 0. So for sure, alpha has to be positive. And about the rest, we don't have information. So for beta, we don't know. For gamma, we don't know. As long as they don't bother us for the purpose of this lecture, is enough. Of course, eventually we could measure more properties of this phase that give us information about beta and gamma, but that's a different business. Right now, we don't know. And finally, when the temperature is much smaller than T star, what do we have? Well, we have to be able to generate two minima, left and right. That's all we know. And we can do this in different ways, as we have a sketch here. So for example, by continuity with these two cases, we could have alpha positive that would correspond to keeping the minimum at P equal to 0. And then it's very easy. If alpha is positive, then I have to come down, and then I have to go up, right? So beta has to be negative, and gamma has to be positive. That's one possibility. If alpha is 0, so if this free energy landscape were to be totally flat at the origin, you still need beta negative and gamma positive, so that's kind of a similar case. And the other possibility is that alpha is negative, so that there we have a maximum at P equal to 0. And then if alpha is negative, well, in principle, we could choose beta to be positive, as we did, let's say, to study the continuous transformation, and gamma would be undetermined. Or we could choose beta to be negative, and then gamma would be positive. Okay, so for a sixth order model like this is all that we can have. Okay, these are our options. Okay, so now that we have this, what do we have to do? We have to select a temperature dependence of the parameters, as simple as possible. All right, compatible with the phenomenon or with the behavior we want to describe. Of course, a simple temperature dependent would be the simplest temperature dependent is not temperature dependent. Okay? And in that spirit, if we inspect all these possibilities, it's clear, well, for T star, we really need this. If we want to keep as many parameters as possible temperature independent, then it's tempting, for example, to look at options like this, where beta is negative, as we need it in T star, and gamma is positive, as we need it in T star, right? Similarly, this option, beta, no, this beta is positive, no, similarly, this option, beta is negative, and gamma is positive, as we need them to be for temperature equal to T star, so those two work pretty well. Also, at high temperatures, as long as beta and gamma don't bother us, every choice is fine. So that all that would also be compatible here. Of course, by the way, we could measure additional properties, for example, nonlinear response, direct response of our material, and say something about beta and gamma at high temperatures, but this is not our topic today. So all that looks pretty good. This option here is a bit tricky because here we need beta positive, which forces us to change the sign of beta as a function of temperature, and we need alpha negative. We would also force us to change the value of sign of alpha as a function of temperature. So if this happens, both alpha and beta have to change sign as a function of temperature. That's definitely not simple. So tentatively, we are going to disregard that one, and we are going to stay with the rest. So the only ambiguity here is that depending on where we are at low temperature, alpha can be positive or can be negative, but everything else is fixed and potentially temperature independent. Okay? So with that in mind, we can propose something like this. I propose to consider the following choice. Alpha prime T minus T0, beta is negative and temperature independent, and gamma is positive. Okay, and alpha prime, by the way, is positive. Now this T0 is different from T star. It's a different temperature. Okay. In fact, when T equals to T star, we need alpha to be positive. So T0 has to be smaller than T star for that to happen. Okay. So alpha at T star would be alpha prime T star minus T0, and we need this guy to be positive. So necessarily T star is bigger than T0. Okay. Interesting. So we are introducing in the problem a new temperature. Now we have two, T star and T0. This T0 is smaller than T star. And then actually, T0 could be either positive or negative in principle. If T0 is positive, we know that for very low temperatures, alpha will be negative. Particularly at 0 Kelvin, alpha will be negative. And therefore, if T0 is positive, eventually we will have a situation where there is no minimum at P equal to 0, and we only have two minima. Okay? So in fact, T0 marks the limit of stability of the phase with zero polarization. Okay, and for T0 positive, if it is a positive number, there will be temperatures where this state is not a minimum. All right. All right. So for the time being, let's just stick to this choice. Let me write it here. Okay. And what we are going to do next is to analyze mathematically this expression, assuming T0 is positive, for the sake of simplicity. Then we can see very easily what happens if it is negative, and see how mathematically we can describe this phase transition and this energy landscape. Okay? Questions?